So trig review from grade 10. Some of you guys just took grade 10 last semester, so you will know. Some of this will be... Okay.
He gave us a week. He taught it to us in a week.
Really? Okay. Well, hopefully the review will kind of refresh your memory a little bit. Okay, so tell me guys, what do you remember from grade 10? What are some of the main things? Cosine and tan. SOHCAHTOA. There we go. Okay, what does this stand for? Kaylin?
Like angle, like sine.
Yep. So we have sine.
Over
Okay, so sine is O over H. So sine of our angle theta is equal to the opposite over the hypotenuse. Maybe I'll just write out the full word. Okay, does this refresh anybody else's memory? What does the ka part of this represent? Okay, so cosine of theta is equal to the adjacent side over the hypotenuse.
What's that thing beside the sine?
So the theta, this is theta, and it represents the angle that we put in there, or the angle that we're looking for. Depends on what we have. And TOA? Tan of theta. Very good. Opposite over adjacent. Okay. So we can use SOHCAHTOA only in one special type of triangle, and that is for right angled triangles only. Okay, there's another thing that we use sometimes with SOHCAHTOA, and that is if I know two sides of a right angled triangle, I should be able to use Pythagorean theorem to find the third. So we also have Pythagorean theorem for right angled triangles. And Pythagorean theorem says that the legs of the triangles squared and added together should equal the square of the hypotenuse. Okay? In non-right angled triangles, we're going to touch on this a little bit later. So for the most part, we're going to be kind of reviewing SOHCAHTOA today and using SOHCAHTOA in our grade 11 stuff. But there are two things that we learned in grade 10 that we can use for non-right angled triangles. Does anybody remember what they are? Just to find missing sides and missing angles? That's still, I think you're thinking just like how to split up a trig ratio from its angle. We use inverse, yeah. But there are some formulas that we can use in non-right angled triangles. Anyone? They're called laws, if that helps you remember. Okay. What's that? Yeah. Sine law and cosine law. And I'm going to review these more in depth once we get to our applications part of this unit. But for sine law, it says that side A over the sine of angle A should be equal to the ratio of side B over the sine of angle B. And it's also equal to the ratio of the last side of the triangle, side C, over the sine of angle C. Okay, and then cosine law can also be used in non-right angled triangles depending on what information we're given. And it is one side squared is equal to the sum of the other two sides subtracted by 2 times the other two sides multiplied, and then times the opposite angle to the side we're looking for. Okay, so we use these in non-right angled triangles. There are cases where we will use sine law and cases where we will use cosine law based on what information we're given in the triangle. Again, I'll unpack those a little bit more in some future lessons. Okay, so it's important for us to remember that we only use Pythagorean theorem ever in right-angled triangles. We can't use Pythagorean theorem in non-right-angled triangles. We can use the laws, and that's pretty much it. Okay? Okay, so we're going to do a quick little review of how we can use SOHCAHTOA to solve for a missing side, and then we'll talk about how we can solve for a missing angle. Let's scroll over to our examples here. Sorry, I'm trying to get this to load. There we go. Okay, so to find a missing side, this angle that I'm given is going to be like my theta. It's going to be my reference angle. And we will label our sides based on that reference angle. So so we need to decide between opposite, adjacent, and hypotenuse. So the side 1, what would this be? Karen? Or Natalie, sorry. Opposite. And x, Kendall, is hypotenuse, yes. Very good. And I know that because it's across from the right angle. And opposite is always across from the angle that you're looking at as your reference angle. So if I have opposite and I'm looking for hypotenuse, which trig ratio should I be using out of sine, cos, and tan? We have opposite and hypotenuse. Kaylin? That would be opposite and adjacent. Sine, not sin, sine. So if sine of theta is equal to opposite over hypotenuse, then I'm going to plug in, so remember my theta represents that angle measurement. I'm going to plug in 30 degrees there. My opposite side is 1, and my hypotenuse side here is x. Okay? Before I start calculating in here, I want to get x by itself. So when x is in the denominator, we did some of this with our inverse type stuff. I can't have x in the denominator, so if I'm going to solve for x, I actually need to multiply it up on both sides so that I can get it out of the denominator on the right-hand side over here. So those will cancel. And I'll have x times the sine of 30 equals 1. And it's important for us to remember as well that when I have the sine of 30, those two guys move together always. They're like buddies. They're kind of glued together. So if I want to get x by itself, I need to divide out this whole expression of the sine of 30 here. And they will cancel out on the left-hand side. Okay, so we're going to calculate. We're going to make sure our calculators are in degree mode. And we're going to calculate 1 divided by the sine of 30 degrees. Okay? In order to make sure your calculator's in degree mode, you can make sure that you get the same answer as us. Just do a little test. But you should have like up in the top, you should have a little highlighted D, or it should say DEG if you're in degree mode. Okay? So let's try that out. If you have any problems with your calculator, raise your hand now so I can come help you. You're fine then. You're going to go to mode, and you are in radian mode, so we're going to want to be in degrees. And then you'll enter. Okay, so you're good.
Okay, thanks.
Okay. So mode, and then you're going to go and highlight degree and press enter, okay? Okay, so you're going to go mode, and you're going to click it until you get here, and then you're going to hit 1. Okay? Anyone else? Okay, now see if you guys can calculate this once you get changed over. Okay, so we're going to go to setup. So we're going to press shift and then this button, and then you're going to hit 3 for degree. Okay? Okay, what did you guys get for this? 2, perfect. So if you're in degree mode, you should get 2 here. If you're not in degree mode, you'll probably get something different. So that should be a good little test to see if you're in degree mode or not. Okay, any questions for this one? We're all good? We can all get 2? Okay. So that's find a missing side. Now let's say we need to find a missing angle. So we are finding theta here. This is going to be our reference angle, which means I want to label our sides accordingly. So I have one side and its measurement is square root of 2, and then the other side is 2. Can somebody tell me what side, opposite, adjacent, or hypotenuse, is root 2? Liam? Adjacent, very good. And 2? Natalie? Is hypotenuse. So which trig ratio should we utilize here to help us solve for the angle? Natalie? Cosine, good. We have cos of our angle equals adjacent over hypotenuse. So I don't know the angle, so it's just going to be cos of theta for now. The adjacent side is square root of 2, and the hypotenuse is 2. Now before I go ahead and calculate this, I actually want to get theta by itself. Does anyone remember, now that cosine and theta are kind of glued together, how do I get them apart if I want to separate them? We use the inverse function. So what I need to do is I need to take the cos inverse, so I'll probably have to press like shift or second on my calculator, and then I'm just going to enter that whole thing into cos inverse. Okay, what did everybody get? 45. 45 what? Degrees, very good. If you got like 1.78 something, you're in radian mode. Okay, so let me know if you need some help switching over. Okay, that is your crash course in SOHCAHTOA. Okay, does that bring back some memories with trig for grade 10? Okay. Any questions on this one before we move forward? Okay, can I scroll? Okay. All right, so in grade 11, we are going to look at the idea of special angles, which come from two types of important triangles. So if you think back to like some of your geometry units in previous math courses, we talked about different types of kind of like special triangles. We talked about, we have isosceles triangles. What is the properties of an isosceles triangle? What makes isosceles triangle special, Karen? Or Natalie, sorry. Yep, two sides are the same length, and because of that, two of those interior angles that match up with those sides are also the same length. And then equilateral, what does that mean? Liam? All sides equal. Okay, so the idea of special angles come from these two types of special triangles that we have. They're triangles that have some certain properties that make them symmetrical, right? Or they make all sides equal. And what we're doing with these special angles is we're focusing on where we can get exact values when I do the sine, cosine, or tan of angles in these special triangles here. So we've been focusing on this a lot in our grade 11 course, but just to remind you, exact values are in fraction and radical form. And exact values do not have decimals. Okay, so there are some triangles where we will be able to get these exact values of the ratio of, let's say, sine of the angle is opposite over hypotenuse, and this will be true for all triangles with those angle measurements. But if I have other angles, they're stored in my calculator. The ratio is stored in my calculator, so when I type in something into my calculator like the sine of 50, I'm getting the opposite over hypotenuse measurement for all triangles that are a right angled triangle with a degree 50. And the opposite over hypotenuse is the same for all triangles with that 50 degree. And that's true because of the idea of similar triangles. So hopefully in grade 10 you were introduced to the idea that if I have a triangle, let's say I have a right angle triangle. You guys don't have to write this, but you can if you want to. And let's say I have an angle that is 35 degrees, making this 55 degrees over here. And I have some side measurements, right? Like let's say this is 2, and this is, well, not 2. This will be lower. Okay, and let's say this is something like 1.5. Okay, any triangle that I draw is going to have the same scale ratio of all sides. So if I use Pythagorean theorem and I find the hypotenuse of this, all of the triangles, whether I scale them up or scale it down, sorry, I didn't want to draw that so big, they're all going to have the same ratio of sides. So as long as this is 35 and this is 55, if I enlarge this by a scale factor of, let's say, 3, this is going to be 6, and this will also be enlarged by a scale factor of 3, and the hypotenuse will be. So the idea is that no matter what side measurements I have, the ratios, once I divide those ratios, I'm going to get the same opposite over hypotenuse for the same sine of 35, let's say, or tan of 35, for any triangle with a 90, 35, 50. 35, 55. So the idea of special triangles is if I were to set up tan, let's say, of 35 in either one of these triangles, I'm getting in the first triangle 1.5 out of, or over 2.5, and my tan of 35 in the second triangle is 4.5 over 6. What are these both equal to? I'm not saying tan 35, but 1.5 over 2 and 4.5 over 6. Kylie's? Yeah, or 0.75. So you notice, guys, no matter which side measurements I have here, every tan of 35 is going to give me out that same ratio in that particular triangle, right? So I actually should have calculated the labels on these, but you guys kind of get the idea. So tan 35 actually isn't quite equal to this. It's equal to 0.7, but you guys get kind of the idea. So yeah, so that's kind of the thought behind this. So we have some special triangles. Liam, again with the headphones. We have some special triangles that we use in order to get exact values, and they come from the isosceles idea. So hopefully you saved a little bit of room here. But they come from the idea of an isosceles triangle and an equilateral triangle, but they are 90-degree triangles. So when we look at an isosceles triangle, I thought I had a label down here. Maybe it didn't load. There we go. There it is. So if I have a 45, 45, 90 triangle, we'll draw it out here. So that's a right angle triangle. I have some standard side measurements that no matter how I scale up or down this triangle, it will always come back to these ratios here. And the idea is that I'm just showing you the triangle that has the smallest side measurement as 1. But I can always scale this up or scale it down. I'm still going to get the same sine, cosine, and tan ratios out of this particular triangle. So what we're doing here is not solving for anything. We have all sides and all angles here. There's no reason that we need to solve for anything. But we're going to set up the ratios of sine 45, cos 45, and tan 45 so we know what their exact ratios are equal to for any 45, 45, 90 triangle. So sine of 45, let's suppose that we make, it doesn't matter which 45 we choose as our reference angle, but I'm just going to choose the bottom for our purposes here. So this will be opposite, this will be hypotenuse, and this side will be adjacent. So what is the sine of 45, meaning the ratio of the opposite over hypotenuse side of this triangle? What is it going to be equal to? Natalie? I thought you just mouthed it. What's opposite over hypotenuse in this triangle?
1 over square root of 2.
Yeah. Okay? So in a 45, 45, 90 triangle, any sine of 45 is going to be equal to this. And it's also stored in your calculator. This is, the 1 over root 2 is the value that's actually stored in your calculator when you type in sine 45. So I want everybody to take their calculator, and I want you to type in the sine of 45. Okay? And some of you, I want you to put it into a decimal for me. I know a lot of your calculators will leave it in fraction form. What did we get as a decimal?
0.7.
Okay, now I want you to tell me what is 1 divided by root 2. Put that into your calculator. Right, same thing, right? So what this is basically telling me is that this value is stored inside my calculator, the sine of 45, but this triangle just allows us to keep it in exact values. I am also aware that some of your calculators are giving you out with this. Probably when you first put in sine of 45, it gave you out root 2 over 2. That's just this expressed in a bit of a different way, but root 2 over 2 is actually that 0.7 value. It's the same value. So this is actually in exact values. Instead of saying 0.7 whatever, we have the exact value for it. It's here. Okay? And I have a little app that I can kind of show you on. It doesn't matter in this triangle if I have, so this one shows me that the lengths of the two sides are equal to 1, 1, and root 2, just as I showed you. But if I scale this up, let's say I make the lengths all, if I scale it up by a factor of 2, so now the lengths are 2, 2, and 2 root 2, my ratios of sine and cosine and tan are actually still going to be the same. So if I have, looking over at this applet here, if I have the sine of 45 in my triangle, so I have a 45, 45, and the length measurements were 2, 2, and 2 root 2. What is the sine of 45 going to be? What's opposite to 45? 2. And what's hypotenuse? 2 root 2. So what happens here with the 2's? So I get what? I get 1 over the square root of 2. And that's the same thing that I just showed you on the first triangle. So it doesn't matter how we scale up or down this triangle. I'm always going to get out for sine 45 1 over root 2. Okay? So that's why this works. All right. So back to our lesson here, which is not this one. This one. Cos 45. What is adjacent over hypotenuse equal to in this triangle? One over root 2, very good. And last one, tan of 45. Tan is opposite over adjacent, so what is opposite over adjacent in this triangle? 1 over 1, which equals 1. So if I sub in tan 45 into my calculator right now, you guys can do it, we should expect to get out 1 from that, because that's the ratio of the opposite over adjacent, and it's already stored in our calculator, right? Okay, so we are going to box these up. I'm going to make a better box that actually is straight. Okay, so you might be asking yourself the question, why am I doing this if it's stored in my calculator? Good question. Everything is actually stored in your calculator for all possible triangles that you could have. But these are just special triangles in particular. And I want you guys to know the reason why we happen to get exact values for these particular sine of 45, cos of 45, and tan 45. I want you guys to know where they come from. Also, if your calculator is not one of the calculators that leaves things like in exact form for you, like it leaves things with radicals and in fraction form, this is how we can get those values as exact values. We are not going to be using our calculators at all for this first part of the unit. We don't need our calculators for this. Okay? So anytime I am looking at sine 45, cos 45, or tan 45. I should be able to set this triangle up with the side lengths. So the side lengths are 1, 1, and root 2 is the hypotenuse. And I should be able to figure out any three of those that I want, sine 45, cos 45, or tan 45. Kylise, do you need to go take a walk so that you can wake up? It's okay. Maybe take off your jacket so that you're not so warm. Okay, does that make sense?
I have a question.
Yes.
What are we learning? What are we trying to find?
So right now we're not solving for anything, but we are finding the exact value of sine 45. So what is sine 45 always equal to, and what is it exactly equal to with no decimals?
It's not the same as like sine 50.
Right.
Like where would we see this being used?
So I'm gonna show you guys some examples of how we can use it. But these are essentially just like, we'll see more applications once we get into our second unit, and then also once we get into like using them in grade 12 as well. But yeah, these are just like special angles that we can get exact values for. Okay, the second one we get from an equilateral triangle. So I'm just going to show you up here. If I have all sides equal in a triangle, what does that mean about the angles? They are all equal. Now, if I have all equal angles, because this is an equilateral triangle, and angles have to add to 180, what are all these angles equal to? 60. So I have 60, 60, and 60. Now you will notice that there's no right angle triangle here. Okay, and that's a problem if we're going to be using a 90-degree triangle. So our next special triangle actually comes from taking an equilateral triangle and cutting it in half. So when I cut it in half, I'm just going to draw it a little bigger for you over here. When I cut that in half, I still have that 60-degree angle in this corner over here. So this is still 60. But I now have a 90-degree angle right there. And if I cut this top 60 in half, what does this angle up here become? 30, that's right. And that's where our 30, 60, 90 triangle comes from. Okay, so the important thing to remember with this triangle is that this first triangle was isosceles, and it had 45, 45, and 90. So it actually had two equal sides. They were both equal to 1. Now this one should have 3 different side measurements because it has 3 different angle measurements. The smallest side in both of these triangles is always equal to 1. How do I locate the smallest side in my 30, 60, 90 triangle? How do you know it's the bottom one? Other than the fact that it looks like the smallest. It's the opposite of the smallest angle. Very good. So across from 30 should always be the side length 1, no matter how I set this up, how it's rotated or whatever. If it's across from 30, it's 1. Now the hypotenuse of this triangle, now let's look back to our equilateral. If this is 1, that must mean that I cut this part in half and this was 1. So if this whole length is 1, what's the full length of the side here? 2. So what's the hypotenuse length? If this is equilateral? 2. So my hypotenuse is 2. And if I use Pythagorean theorem to solve, you'll see that for the third side we would get the square root of 3.
So we have to solve that.
If you forget, or you can just remember the side measurements. So these triangles, these 2 triangles, there's only 2 of them. These are kind of a remember thing. Either a memorize or a understand and know type thing.
There's only 2 special.
Only 2. That's all I expect you to remember. Okay? So smallest side in both of these triangles is always equal to 1, and then you can work from there. Okay? So we're going to set up 2 different sets here. We're going to set up sine of 30, cos of 30, and tan of 30. And we're also going to set up sine of 60, cos of 60, and tan of 60. So let's start with all the 30s. 30 is going to be my reference angle. Okay? So if 30 is my reference angle, this is opposite, this is adjacent, and this is hypotenuse. So can somebody tell me what the sine of 30 would be equal to in this triangle? What is the opposite over hypotenuse in our triangle? 1 over 2, you got it. And how about the cos of 30 in this triangle? What's adjacent over hypotenuse? Root 3 over 2, very good. And tan of 30? Opposite over adjacent, what would that be equal to here? 1 over the square root of 3. Okay, box those guys up. Those are another set of special angle values. Okay, and then my last one is going to be all the 60s. So I'm going to switch my reference angle from 30 to 60. And if I switch my reference angle, the labels on the opposite and adjacent sides also must change. So if I switch my reference angle to this, what is opposite to my reference angle now?
3.
The root 3 part, right? This is now opposite, and this is now adjacent. Hypotenuse doesn't change because it's across from the 90. So let's set up sine of 60, cos of 60, and tan of 60. Okay, can somebody tell me what sine of 60 would be in this triangle? Natalie?
Root 3 over 2.
Very good. Root 3 over 2. That's opposite over hypotenuse. Cos of 60? Yep, 1 over 2. Very good. And tan of 60? Root 3 over 1, which ends up being just root 3. Okay, box those guys up as well. Okay, that's my last set of special values. So guys, I do not have to memorize all the things in boxes here. I need to know the triangles, and by knowing the triangles, I should be able to find any one of these that I want to use in a question, or if I simply just ask you what is the exact value of the cos of 30, you should be able to draw the triangle, use 30 as your reference angle, and say, oh, my adjacent over hypotenuse, if 30 is my reference, is root 3 over 2. So the exact value of cos 30 must be root 3 over 2. No calculator needed, right? Joey?
I'm still confused about how each side, like I took the length of each side.
So the lengths of this triangle's sides, the smallest one we set equal to 1, but I can scale it up or down. I could make it 2, but the hypotenuse is still going to be, it's still going to have all the same side ratios. So like I showed you over on this little app here, if I'm looking at, let's look at the 30, 60, 90 triangle. I can make my side measurements, I can set the smallest side equal to 1, right? So I'm using my slider here. I set the smallest side equal to 1. Oh, no. There you go, 1. And then my other side is going to be root 3 and 2. That's just how the Pythagorean theorem works, right? That will always be the side lengths of this triangle. If I scale it up, I'm still going to have, you'll notice that I have the same ratios of the sides still, right? Like I have 3, and then it's 3 root 3, and then instead of 2, because I've tripled it, it's now 6. Okay, so all triangles that are 30, 60, 90 have these scale ratios of their sides. Okay? If you don't believe me, you can check with Pythagorean theorem. Okay, so let's see how we can use these things. Do we want to take a quick 2-minute break first? Okay, 2 minutes, and then we will continue. So, you may be asking yourself, what are we going to use all of these things for, right? So, anytime I see a 45, a 30, or a 60 as an angle, I'm going to aim to leave things in exact value. That's kind of the point of this. If I see any other angle, I'll use my calculator and we'll just get the value of it. So in this case, I have a triangle and we're asked to use special triangles to find the values of all sides and angles. So I should be able to use the idea of scale ratios or similar triangles to find the rest of these without even having to do really like any trigonometry related math. So if I know that my special triangle, the most basic form of this triangle is my 45, 45, 90 triangle, and I know the side measurements are what I showed you above, 1, 1, and root 2, I should be able to pinpoint, if I just am given the length of at least one side, I should be able to pinpoint the scale factor that this triangle over on the left is being enlarged by from our original triangle. So how would I possibly get from 1 to 4? What is the multiple that I'm using there? Okay, Lise? Times 4. So if I take each side and I multiply it by 4, I should get the rest of the sides in this triangle. So this side over here matches up with this one. So what should my other leg of my triangle be equal to? If this one is 1, this one's equal to 4 centimeters. Good. And if this one is root 2, what's my hypotenuse in the new triangle? 4 root 2. Perfect. And what's the remaining angle in this triangle? 45. Very good. And we're done. We have all sides, all angles. I didn't even have to use any trig or anything. Pardon? Yeah. That's it. Okay? And you will notice here, guys, if I ask what is the sine of 45, you don't have to write this down, but just so you guys know, if I use this as my reference angle, opposite over hypotenuse in my triangle would end up simplifying to 1 over root 2. So any version of this triangle, the sine of 45 will be equal to 1 over root 2, no matter how big or small it is. So that's kind of the idea of your special triangles. Okay, let's do special triangles again here. Okay, so we're going to use special triangles, but this time we have a triangle with 60 degrees. So I want to use my 60, 30, 90 triangle. And I'm going to rotate this a little bit because in the original one that I showed you, you'll notice 30 is at the top. Now I want 60 to be at the top because I want it to match with the way that this triangle, the original triangle, has been ordered. So if that is 60, my remaining angle on the bottom right here is 30. And I always have to make sure that across from 30 degrees is what side measurement? What was that? 1. So across from 30 here, I need to make sure I always label that side equal to 1. So it doesn't matter which order I put them in, as long as I label the sides properly. What is across from 60? What's the side measurement there? Root 3. And what's the hypotenuse of this triangle? 2. Lovely. Okay, so I put this in a similar order to how this one was arranged, just so that we can see what is happening to get from root 3 to 3 root 3. So what's our scale factor here? Natalie? Yeah, it's multiplied by 3. So I should be able to take all of these sides here and just multiply them by 3 and get all the sides of my new triangle. So if I take 1 and I multiply it by 3, this side is now 3. And then if I take my hypotenuse here and I multiply it by 3, that side, the hypotenuse side of my new triangle, is now 6. And what's the remaining angle in here? 30. Great. Perfect. Good? Okay. We can also use it to determine the exact values of expressions. So what we're going to do here, guys, there's lots of different trig ratios in here. We are going to use our triangles, and we're going to actually replace each of these guys with their exact values. So no calculator needed. Sine of 45. So we have the triangles already drawn for us anyways, but I'm just going to show you in here. If I were doing this question by myself, I would be drawing my triangle that's related to 45, and then I would be labeling my sides. So remember, this is like a memorize thing. We want to know these triangles. And I would be saying, okay, if I use 45 as my reference, this is opposite, adjacent, and hypotenuse. And then I would say to myself, okay, what is the sine of 45? Well, if sine uses opposite over hypotenuse, the sine of 45 is equal to 1 over root 2. And I would replace the sine of 45 with its exact value, which is 1 over root 2. Okay, and then I would look again at my 45, 45, 90 triangle, and I would say, okay, what is the cosine of 45? Well, cosine is equal to adjacent over hypotenuse. So the cos of 45 is equal to 1 over root 2 again. Okay, the second part of this uses the 30, 60, 90 triangle. So I'd be drawing my 30, 60, 90 triangle. Okay, I know we drew them above, but it's good to start to draw them to remember them. I would label my sides properly, remembering that 1 should always be across from 30, and root 3 is across from 60, and 2 is the largest side, so it's across from the largest angle, which is 90. And then I would say, okay, I'm using sine of 30 in this first one. So I want to know from 30 as my reference angle, what is opposite to that, and what is hypotenuse. So opposite is 1, and hypotenuse is 2. So I would replace the sine of 30 with what? 1 over 2. Good. And then my second part of this asks me for the sine of 60. So I would change my reference angle in this triangle to 60. And then I would say, okay, what is opposite over hypotenuse if 60 is my reference? Well, if 60 is my reference, then opposite to that is root 3, and hypotenuse is 2. So I would replace sine of 60 with root 3 over 2. Okay, we're not using any calculators here. Okay, now I just need to simplify this expression. So I'm going to follow BEDMAS. I want to do all multiplications first, and then we'll do additions. When I'm multiplying fractions, I don't need common denominators. That's only when I'm adding and subtracting. So I just multiply the numerators. I'll do 1 times 1. And then I'll multiply the denominators. Root 2 times root 2. Can someone remind us how we multiply roots or radicals? What do we do? We just multiply the numbers under the radical and leave the radical part. So root 2 over 2 is like root 4. Okay? And then 1 times root 3, that just gives me back root 3. And 2 times 2 gives me 4. Okay? Can I simplify the square root of 4? What's the square root of 4? It's just 2. And then my last step would just be to actually add these and put them together. So in order to add 2 fractions, I actually need a common denominator here. So I want to make, I think our common denominator can be 4. So if I want to make this side equal to 4 on the denominator, I have to multiply by 2, and I must do the same thing to the numerator. So I now have 2 over 4 plus root 3 over 4, and I'm just going to merge these guys together in one fraction, and I will be done. Okay, that would be my final answer. Okay, any questions on any steps that I did here? Okay, so if I want to evaluate an expression, I'm replacing, I have to have 45s, 30s, and 60s, otherwise I can't do exact values. But I will replace them with their exact values from the triangles, and then I'll just work to simplify that expression as much as I can. Okay? Okay, there's one thing that you might see in your travels, and I want to make sure that you guys know how to do it, just in case you happen to come across it. If you have one of these calculators, like the black ones or the gray ones that have the orange buttons and they leave your stuff in radicals, this will explain to you why you get certain answers in this calculator. Because technically, as mathematicians, just like mathematicians don't like negatives in their exponents, they also don't like roots in their denominators. So the process of rationalizing the denominator is we remove roots from the denominator. And your calculator does this automatically, but again, I want you to know why your calculator is giving you out the certain things that it is. And I want you to be able to do it yourself as well. Because if we happen to have a variable later, maybe in like advanced functions or something, and we're working with a variable that's in the denominator, I can't just put it in my calculator, right? So I want you guys to know the process so we can use it with more complex things in the future, and so you know why your calculator is spitting out what it is. Okay, so if I have a single term in my denominator and it's a root, all I need to do to rationalize the denominator is multiply the top and the bottom by that root. Okay, by multiplying the top and the bottom by this, I'm really just multiplying by 1, because I'm multiplying by root 2 over root 2, which is 1. So I'm not changing the expression in any way, I'm just expressing it in a slightly different format. So I'll have on the top 2 root 2, and what always happens on the bottom is I get a root which can be square rooted to give us a number. So what's the square root of 4? We just said it in the last example. 2. And I can actually now simplify this because I have 2 over 2 here out front. And 2 divided by 2 is actually just 1. So I'm just left with root 2 here because the 2's cancel. Okay, and now there's no roots left in the denominator. So that's also why you guys notice that when we had sine of 45 was equal to 1 over root 2, your calculator rationalizes that denominator for you. And it says, okay, I'm going to multiply the bottom and the top by root 2. And then I'm going to get root 2 over the square root of 4, which we know is 2. And that's why your calculator gives you out root 2 over 2 for sine of 45. Okay? This is helpful if you're finding exact values of expressions. This is actually helpful to enter in these expressions with the denominators already rationalized. And it will prevent you from having to do that. Typically, it will prevent you from having to do that at the end. So if you'd like, you can go back up to your little list that we did up here, and you can just show these things with the denominators rationalized. I will accept either one of these answers, but these are especially good if you are evaluating like the exact value of expressions like we did in example 3. Okay, so these are the rationalized versions of these. And then also we have another one over here, which is 1 over root 3. And the rationalized version of that is root 3 over 3. Okay, so you will notice if you put them in your calculators, any 3 of those, it will give you the version in the blue that I just wrote for you there. Okay, so if you want to add that to your sheet, you can add that. Okay, so we're almost done for today. I just want to show you as well, if we are rationalizing, there you go, there it is. If we're rationalizing something that has an addition or a subtraction in it, we have to do it a slightly different way. And the way that we do this is we create almost like a difference of squares. So I'm going to multiply the top and the bottom by the exact same expression, except what I do here is I actually switch the sign that I see. And you will see when I show you how we FOIL this out on the bottom, you're going to see why we did that. So off to the side, I just want to show you what happens when we now FOIL these 2 expressions on the bottom. So what happens is I do 3 times 3, and it gives me 9. And then I do 3 times negative 2, and it gives me negative 3 root 2. And then I do 3 times positive root 2, which gives me positive 3 root 2. And then I do positive root 2 times negative root 2, which gives me negative root 4. And the square root of 4 is 2. So what happens with the negative root 3 root 2 and the positive 3 root 2? They cancel. So I now don't have any roots left, right? So I actually just get 9 minus 2 here, which simplifies to 7. So this will always happen when I have an expression that is something plus something. If I multiply by the reverse of that, something minus that something, the roots end up canceling out, and it works out really well for rationalizing. So that's why we do that. So we'll end up with 2 times 3 minus root 2 all over 7 as our final answer here. And that would be the answer that your calculators, if they leave in radical form and fraction form, that would be the answer that your calculator would spit out to you. Joey?
Would it be wrong if you plugged it 2 into the brackets?
We usually, if we're like simplifying, we usually leave things in common factored form. So no need to do more work than we need to, right? So we'll leave it usually common factored. Okay, last question. We're almost there. Any other questions before I move forward with this? Okay. Last one, we're going to prove that the sine of 60 over the cos of 60 is equal to the tan of 60. So let's draw the triangle that we are going to use for this. It's the 30, 60, 90 triangle. I know that because there's 60s in all of my trig expressions. And I want to make sure across from 30 is 1, across from 60 is 3, and the hypotenuse is labeled as 2. And because we're dealing with 60, I'm going to use that as my reference angle, and I'll label opposite, adjacent, and hypotenuse based on 60 as the reference. And we're going to start by just plugging in the exact values of each 3 of these expressions. So let's start with the right side. What is the tan of 60? What's its exact value? What is opposite over adjacent if 60 is the reference? Natalie?
√3/2.
Close. Opposite over adjacent for tan. √3, yeah. Just ends up being √3/1, which is √3. Okay, what about sine of 60? Natalie? √3/2. Very good. Did you think that's what I was starting with? And cos of 60? I need adjacent over hypotenuse in my triangle. Cos of 60, 1/2. Very good. Okay, so now my job is just to prove that when I simplify on the left side over here, that I end up getting the square root of 3. I end up getting the same thing. So what do I do when I'm dividing two fractions? What's the rule? Flip both of them or one of them? Just the second one. Okay, good. So I'm going to flip the bottom, and then I can change to multiplication. And do you guys notice what's happening now on the left side? Kaylin, what's going on? Yep. Yep. These are now canceling, and what do I have left? Just √3, and technically it's over 1, but we know √3/1 is just √3. So now I have proven that these two expressions are equal, right? Sine of 60 over cos 60 is actually equal to the tan of 60. So we're good. Left side is equal to right side. Great. Okay. Let's stop this.